All right.
Cool.
So Zenin is currently a PhD student in the Joint Center for Quantum Information and Computer Science and Department of Computer Science of University of Maryland, College Park. He's broadly interested in quantum information science and is working with Andrew Childs and Alexei Gorshkov. Prior to that, he obtained his master in physics from ETH Zurich in 2022 and his bachelor in natural science from Durham University in 2019. Let's all welcome our speaker.
Thank you. So may I start?
Yes, please.
Cool. So thank you very much for the invitation and introduction. And hello, everyone. I'm Zhenying Liu. I'm currently a PhD student, and today's talk is about depth-efficient proofs of quantumness, which is a joint work with Andrew Golgiu, who is currently an assistant professor at Chalmers University. And this research was conducted when both of us were at ETH Zurich in Switzerland. So let me start by the motivation of the work. As we all know, quantum computing is developing rapidly in recent years, but we're still in this so-called noisy intermediate scale quantum era, or the NISQ era, which means that we only have quantum devices with up to 100 qubits, and we're not able to perform fault-tolerant quantum computation. So in this case, a very interesting question is, does NISQ devices also have some kind of advantage over classical computers? And if so, how can we show that? A general idea is asking the quantum devices to solve some classically hard computational problems. And if they can do it in polynomial time, then of course they have some sort of advantage. So what problem can we use? One candidate is factoring. We know factorization of large integers is believed to be intractable for classical computation. And as we all know, there's a famous quantum algorithm called Shor's algorithm. It can solve it in polynomial time with high probability. But this is not really feasible for NISQ devices because factoring large integers using Shor's algorithm would require a huge number of qubits, which is clearly not doable at the moment. So what else can we do? A quite popular idea is about using the sampling problems. There are some probability distributions that are hard to sample from for classical computers, but we have some quantum approaches to efficiently produce samples from those distributions. For instance, there are boson sampling and random circuit sampling. And those tests of distributions are actually quite successful, as we all know. There have been several experimental realizations of random circuit sampling using superconducting qubits, including the first claim of the so-called quantum supremacy. And boson sampling has also been implemented by the USTC group. So all of these groups claim that it would take really long time of classical computation to achieve the same result, while it only takes very short time using their quantum solution. Therefore, it shows some kind of computational advantage. However, not everyone is satisfied by those results. One question we can ask is how do you test if the sampling is performed correctly? So what they did is kind of statistical tests on the output, which is slightly different from the sampling task itself. We know sampling is hard, but we're not sure if passing the tests is equally hard. And in those works, they just assumed it is. So this is actually another computational assumption. We call it the hardness of spoofing. And it is not as plausible as the hardness of sampling. And furthermore, performing those statistical tests would generally require exponential time classical computation, so they don't scale very well. And that's also part of the reason why most current implementations are below 60 qubits, because larger samples cannot even be verified. So now you might ask, is it possible to demonstrate quantum advantage without those troubles? And the answer is yes. And the key is to use another idea called interactive proofs. Interactive proof is used in various situations, and the one to show quantum advantage is usually referred to as proof or test of quantumness. Well, it's worth mentioning that the proof of quantumness idea originates from a famous previous work about classical verification of quantum computation, which was done by Mahadev 5 years ago. So now, let's see what a general proof of quantumness looks like. So I will just call it POQ in this talk afterwards for simplicity. POQ is an interactive protocol between a classical polynomial time verifier and the self-claimed polynomial-time quantum prover. So the verifier aims to see if the prover is indeed doing something quantum. She does it by sending a number of challenges to the prover and asking for answers from him. If the prover can pass the challenges with a frequency greater than some threshold frequency or probability, then the verifier can say with rather high confidence, the prover is indeed performing quantum computation. So let me introduce the two defining properties of POQ protocols. The first one is called soundness. That is essentially the threshold probability that I mentioned before. It's defined as the maximum probability that any classical polynomial-time prover may succeed in the challenges. And the other one, completeness, is the probability that a quantum prover succeeds in the protocol if he follows the correct strategy. So clearly, it must have completeness strictly larger than the soundness to be a valid POQ protocol. And we can simply say the prover is indeed quantum if it succeeds with a frequency significantly greater than the soundness or the threshold probability. Okay, so before introducing a specific implementation of POQ, let me first explain the computational assumption that those protocols rely on. It's also the most important concept here. It's called trapdoor claw-free functions. So we'll simply say TCF in this talk. TCFs can be constructed based on various computational assumptions, and there are some 2-to-1 functions. So every element in the range of the function has exactly 2 preimages. We'll say x0 and x1. We'll say x0 and x1 form a claw if they are both the preimage of the same y. And the values of the TCFs can be efficiently computed, so it's also called easy to evaluate. However, this function is hard to invert. I mean, given any image of the TCF, there doesn't exist any polynomial-time classical algorithm to find either of the claw. And it's also called claw-free, which means that given any one element of any claw, it's classically intractable to find the other one. And next, we can see the name of the TCF, trapdoor claw-free function, suggests that they have a special property called trapdoor. Trapdoor is some information that can be used to efficiently invert the TCF. So given any y in the image, one can efficiently find x0 and x1, the claw, with the help of the trapdoor. It's also important to know that the trapdoor is a secret information, so only one party of the protocol holds the trapdoor. And if she doesn't disclose it, then no one else would know it. The final property of TCF is the last one, is an optional one, that is adaptive hardcore bit. So if a TCF has this feature, it's called a strong TCF. And it's a pretty important feature, and I will discuss it later on because it's a bit too technical. Okay, now we have all ingredients to introduce the first POQ protocol. This protocol was proposed by the Barkersky et al. Paper, the BCMVV paper, roughly 5 years ago, and is the one that we will mostly discuss in this talk. So in this protocol, the TCF is strong and is constructed based on the learning with errors problem, or the LWE problem. This LWE problem is a cryptographic problem that can be has been well studied and is firmly believed to be hard. So let's see the protocol. The classical verifier first generates a sample of the TCF together with the trapdoor. So she has the trapdoor, but the prover doesn't have it. Then she sends a description of the function to the prover, but keeps the trapdoor secret. Upon receiving the TCF, the prover is expected to send a y, that is an image of the function, back to the verifier. And next, the verifier has two options. She can toss a coin to decide which one to take. She can either ask the prover to provide any one of the two preimages of y and test if it's indeed the case. This is called preimage test. Otherwise, she may ask the prover to report a binary string D and test if D satisfies the equation shown here. Here, the dot means bitwise in the product. X0 and X1 is the claw corresponding to the Y that was sent before, and the XOR is bitwise XOR. So the verifier here is able to test it because she has a trapdoor and she can invert the function. Okay, so the soundness of the protocol is that 2 times the frequency of passing the equation test plus that of passing the pre-image test is less than or equal to 2 for any classical challenger, any polynomial-time classical challenger. So such a soundness relies on the adaptive Hardcore bit of the strong TCF I mentioned before. It simply means that it's intractable for a classical computer to produce simultaneously an pre-image X together with the string D satisfying the equation here. Well, it was actually shown that if some classical computer can pass both pre-image and equation tests with high probability, then it would be able to break the adaptive Hardcore bit. Therefore, it can break the very fundamental computational assumption that is the hardness of LWE in this case. So this would be an extremely surprising result. Now, okay, we have known this protocol is sound against classical challengers. So how about quantum provers? How can the quantum provers, if they are honest, how can they succeed in this protocol? The key is that the quantum computer can evaluate the TCF coherently. So at the beginning, he can apply Hadamard gates on all qubits of the X register. So he can prepare a uniform superposition of all possible pre-images. Then the TCF can be evaluated coherently and stored in the Y register. Then to produce an image, the prover just measure the Y register in the standard basis. And we can show the post-measurement state is just an equal superposition of the claw corresponding to the measured value Y. So it's just the superposition of x0 and x1 such that fx0 equals fx1 equals Y, which is pretty nice. So now let's consider the tests. For the pre-image test, the prover just need to measure the very nice post-measurement state in the X register in the standard basis and report it. And you can see the success probability will just be 100%. For the equation test, the quantum prover can also pass for sure. He can simply measure the X register in the Hadamard basis. And you will be able to show that the outcome binary string D of this Hadamard measurement will automatically satisfy the equation here. So let's finally summarize the soundness and completeness of the protocol. As we mentioned before, for the classical case, the sum of this formula is up to 2. And if a quantum prover follows strategy outlined before, then he would succeed for sure, and the sum would be 3, which is strictly larger than 2. So it's a valid POQ protocol. And as mentioned before, this protocol presented here is only based on strong TCF. So a soundness requires adaptive Hardcore bit, but adaptive Hardcore bit is not common among all TCFs. But fortunately, there's another protocol that doesn't need adaptive Hardcore bit at all. So this protocol is quite similar to the first one, except that they need to add one extra round of interaction. So this actually opens the door to other computational assumptions apart from LWE and maybe Rabin's function or ring LWE, etc., etc. But in this talk, we will just focus on the first protocol that requires strong TCF for simplicity, but actually our results would also automatically apply to the second one that works for other computational assumptions. Okay, so to summarize the pros and cons of POQs, they only require one plausible computational assumption, which is using the construction of TCFs, and we can verify the results in polynomial time, but it also has drawbacks. The coherent evaluation of TCFs generally requires polynomial depth, or at least log depth quantum computation, which is not suitable at all for NISQ devices. Now you might ask, is it possible to somehow bridge the gap and make it more suitable for near-term devices? Well, as we all know, that a necessary condition for NISQ computation is that it must have small circuit depths. And this is exactly the topic of this paper, of this talk. We aim to show that it is possible to run POQ protocols on constant depth quantum circuits. The general idea, as I pointed before, is to evaluate the TCFs in constant depths because all other steps are already constant depth. And in this project, we will just give 2 approaches. One is generic and the other one is specific. Before I started, it's interesting that there's actually another independent work that appeared just 6 weeks before ours, in which they also proposed a protocol for constant depth POQ, and they use slightly different approach related to measurement-based quantum computation. So now let's get started by the first construction, which is the generic construction. This first construction is based on a cryptographic technique that is called randomizing encoding. So for function f, its randomizing encoding f hat is another function that is an information theoretic equivalence of it. Well, it is called randomized because the new function has some random inputs denoted by R. And our work on POQ protocols rely on two theorems from previous works. The first one is from this AIK paper in 2006, where they said any function that can be computed by log depth circuits features a specific type of randomized encoding that only has constant depth. The other one is a recent result that every existing TCF can be implemented by log depth circuits. So if we just combine both theorems, we will see that every existing TCF features constant depth randomized encoding. And our goal is simply to let the prover evaluate the constant depth randomized encodings instead of the original TCFs. And we only need to see if this new version is still a valid POQ. Okay, now let's see some important properties of the randomized encodings. So here in this graph, we have the original function f on the top, and this randomized encoding f hat is at the bottom. So the domain of f hat is larger than that of f, because the domain of f hat has some randomness inputs. And the codomains are also different for any non-trivial randomized encoding. Randomized encodings have some features. The first one is given any f hat and any y hat that is in the image of f hat, its corresponding y can be uniquely and efficiently computed. So this is called a perfect correctness. And on the other hand, if x is fixed, then for any randomness input r, it corresponds to a unique y hat. So this is called unique randomness. And the last key feature here is that one cannot learn any more about x from y hat than from y. So it means that no information of the pre-image is leaked by the randomized encoding, which is called perfect privacy. Okay, now let me present a central theorem that we have proven in this part of the paper. The AIK construction of the randomized encoding of a TCF is still a TCF. Well, as we all know, proof of quantumness protocols rely on the properties of the TCF. So if all properties are preserved by this randomized encoding, we can say the new protocol using randomized encoding is still a valid proof of quantumness. An important building block of the theorem is the lemma shown here. It basically says if x0 and x1 is the claw of the original TCF, then for any specific randomness input R0, there must be a unique R1 such that x0 R0 and x1 R1 form a claw of f hat. Therefore, the claws are preserved so the test can be performed correctly. We proved this lemma using the unique randomness and perfect privacy properties of randomized encoding. So it's actually a general property of all perfect randomized encoding of TCFs. So as I said, the AIK work proposed a constant depth construction of randomized encodings. So let me briefly introduce their technology. They use a tool called Mod2 branching program, or Mod2BP. In Mod2BP is a problem that computes the number of paths in a directed graph from the point S, or the starting point, to the point T, modulo 2. The number of paths modulo 2. It has an input vector of 0 and 1. So, well, for instance, here, if x1 is 0, then all edges marked by x1 cannot be used in counting the number of paths. But those marked by not x1, like from 1 to t, are available to use. So for the example here, if the input vector is 0, 1, 1, there's only one possible path from S to T, which is S1 to T. So the output of this Mod2 branching program will be 1. Okay, now you might ask, how is this related to our TCFs? The answer is this very important theorem. It's called Barrington theorem. It says that any Boolean function of circuit can be computed by a branching program with a size exponential in the depths of the circuit. So we can see if the depths of the original circuit is logarithmic, then the size of the branching program will be polynomial. Okay, so the remaining construction of this constant depth randomized encoding is maybe too technical to be presented here, but the basic scheme is to convert the function to many branching programs, which means that convert the TCF to many branching programs. and they can be represented by some adjacency matrices, and the elements of the matrices can be somehow further transformed to something that only require constant depth computation by introducing some randomness into it. And these final matrix elements just form the constant depth randomized encoding. So the final constant depth randomized encoding is just the elements of the final matrix. Okay, well, although we don't have time to show the construction in detail, we can still have a look at the resulted classical circuit. So here we show the sub-circuit that computes a single output bit of the randomized encoding. It contains only AND and XOR gates, and it only depends on at most 4 input bits. So the depth here you can see is clearly constant. And the real circuit in the end will be a huge number of this kind of sub-circuits piled together in parallel, because the randomized encoding in the end has many, many output bits. A note here is that every input bit might be used in multiple sub-circuits in parallel. So there must be a copy gate in front of them. Well, this is not a problem in the classical case because you can easily copy any value in the classical case. But it might be a trouble if you think of the quantum circuit. So now let's see how to evaluate this f hat coherently in the quantum circuit. Now from now on, we just use x hat to represent the concatenation of x and r as the pre-image of this randomized encoding. So the prover now is supposed to prepare a uniform superposition of x hat instead of x and evaluate the randomized encoding using the same circuit below. Well, of course, we need to convert this classical circuit into a quantum version, but that is not hard. You just need to follow the instructions here and double the circuit depth to decompute it. So the only remaining problem is actually just the copy gate, as I mentioned before. We know it's not possible to clone quantum states due to the non-cloning theorem, but actually you can still let many gates controlled on the same qubit at the same time, and the solution to that is GHZ states, or GHZ state, or the CAD states. So we know the bits of this x hat will be used repeatedly, so we need to prepare every bit of them as a GHZ state at the beginning instead of naive plus state. So here we use bar to represent the repetition. So it's like in error correction where every logical qubit is represented by a number of physical qubits. Therefore, they can be used in many controlled gates at the same time. Now, one question you might be worried about is if arbitrary size GHZ states can be created with constant quantum depth. And the answer is yes. You just need to first perform some constant depth quantum computation and measure some of them, some of them simultaneously. And then you perform another constant depth quantum computation conditioned on the measurement outcomes. So in this case, we call this approach or this trick quantum classical interleaving. We just need to do it for once in order to prepare this GHZ states of arbitrary size. Okay. Now finally, let's see what this constant depth version protocol looks like. It's really similar to the original one, except that we need to replace the TCF by its randomized encoding, which is still a TCF, luckily. And we need to replace x and y by x hat and y hat. Now we can see that pre-image test still works for sure, but the equation test is problematic. If we check the equation here, we recall that the x hats are concatenation of x and r. Well, the verifier can easily recover y from y hat, as we know. And using the trapdoor, she can further invert the TCF and find the claw, x0 and x1. But in performing the equation test, the full pre-image x hat is required, which contains not only x, but also r. So we got a problem here. Is it possible to recover the randomness input r from y hat as well, if we only know x? The answer is yes. And this lemma here is another important result of this part of the paper. We managed to show that for the specific randomized encoding used in this work here, there exists an efficient classical algorithm to find R if y hat and x are given. Well, this lemma is part of our main theorem that randomized encoding of TCF still a TCF, but it is not universal. We only show it for this construction because it's good enough for us. So now let's finally summarize the pros and cons of the first construction. We now have constant quantum depth, and the depth is just constant values. They are 13 or 15 depending on the type of the TCF you use. However, it has some drawbacks. The major drawback of this construction is that the resulted circuits are too wide. It means that huge number of qubits are required. For our naive example here, where TCFs are built on LWE problem, the width is a large polynomial of the input size. So even though circuit depth is reduced, it's still not suitable for near-term devices. So here is lambda to the power of 33, which is crazy. So what can we do to address these problems? First of all, we firmly believe that this first approach can be improved. It's very likely that the branching program used in this randomizing coding can be constructed much more efficiently, especially for some specific TCFs or for fixed input size. And furthermore, branching program isn't the only way of constructing randomizing codings. We have heard that the Rabin's function x squared mod n may have a linear-sized randomizing coding, but we haven't checked if it's true or it would be helpful for us. But anyway, we didn't investigate too much in this direction, so we just leave it as an open problem. We instead have another idea that leads to our second construction. It's not a generic one, but it is able to reduce the circuit width as well. It's basically to compute a specific strong TCF in phases, which is based on, and this TCF is based on learning with rounding, or LWR. All right, let's get started. Our first result is that we can indeed construct such a strong TCF based on LWR. The form of the function is shown on the screen. Here we separate the input x into two parts, that is b and x, where b is just a binary bit and x is a vector. So the function is essentially a rounding over p of some matrix vector multiplication and vector addition. So the rounding here can be simply understood as taking the first log p significant bits of the number in it. It's also important to know that all arithmetic inside the rounding is performed on the mod q field. And it should also be easy to see that the clause here are just like 0x and 1x minus s. And finally, on our choice of parameters shown here, the hardness of this LWR-based TCF is equivalent to LWE, that is learning with errors. LWE was used in the very first protocol, and as I said, has been well studied. So what I want to explain here is that we are not introducing any new computational assumption. Although we call this TCF based on LWR, it's still essentially based on LWE. Okay, now let's see why we think this phase operations can help us evaluate the TCF. As I said, the TCF contains only mod q arithmetic. And the phases are essentially some trigonometric functions that, as we know, have some intrinsic periodicity. So this mod q and phases are something of similar structure. And if we want to imprint some phases to a state, what we only need to do is to perform some z rotations. And z rotations are commutative rotations. So it's possible to parallelize all of them and make it constant depth. Now, how exactly do we encode some information in phases? We call this technique phase encoding. Like for some integer g that is up to q minus 1, its phase encoding is shown by the equation here. So the number is encoded as a relative phase between the 0 and 1 states. And more intuitively, you can see the phase encoding of all possible. You can see the phase encoding of all possible values of g on this unit circle here, which is also a equatorial cross-section of a Bloch sphere. So in this example, we use q equals 12. Well, obviously, the phase encoding here can be created by applying the R0 rotation on the plus state. Okay, now we have know how to encode a single value as a relative phase. So what about the whole function? We know its output, the output of the whole function is a vector of many components like this. So the TCF is defined like this. So let's use G to represent the expression inside the rounding. And our aim is actually to encode every component of G by phase encoding. And very interestingly, in the end, we will later see that there is an approach to recover the value of F from the phase encoding of G. Okay, now let's proceed. Gi is the ith component of the vector, and we use phi I to encode it as we shown before. And phi, the phi state, is the phase encoding of all m components, which is just the tensor product of all phi I states. Finally, recall that we plan to evaluate the TCF coherently, which means that we need to prepare such a psi state. And for the purpose of this paper, the evaluation should be done in constant depths. So now the question is how we can do this. The answer is again using the GHZ states. Well, recall that in the randomized encoding case, we also use GHZ states, but in that case, we only use that for the pre-image register. But here, we also need to use it for the Z register or the image register. That's the way of doing that is essentially replacing the plus state using the original phase encoding by a large GHZ state. So a key observation here that why we can do this is that in this case, if you use baked GHZ states, it doesn't matter which qubit of the GHZ state that the RZ rotation is applied to. Because in this case, they will all become the relative phase between the whole 0 bar state and the 1 bar state. For this reason, we can parallelize the matrix vector multiplication by RZ rotations on different qubits of the GHZ. So as long as the GHZ state is sufficiently large, we can do all of them by a depth 1 circuit. So the two subcircuits below here tell us that how to do it by controlled RZ gates. So the xjk here stores the case significant bit of xj, and zil is the 11th qubit of the GHZ state that stores the phase encoding of Gi. Now we are able to perform the evaluation in constant depth, and we can create the phase encoding of phi from G. But recall that our goal is, in the end, is to recover the value of fx from the phase encoding. So the question right now is, how can we do that? The solution is not very straightforward, so I need to explain this step by step. So let's take one component Gi as an example. So here, still we use q equals 12. Obviously, in this case, in order to decode, we shouldn't do standard basis measurements because in this case, we will always have a half probability of getting 1 and a half probability of getting 0. So we cannot get any information from it. Now let's take a look at the unit circle. We can see that if the phase in the right-hand side of the circle, then it simply means that Gi is less than Q over 2. And if it's in the left-hand side of the circle, then it means that Gi is greater than Q over 2. Now we can consider the following question. Can we learn whether Gi is less than or greater than half of Q? And the answer is yes. We can do it by Hadamard measurements. We can express the phase encoding in the Hadamard basis, and we will be able to see that the probability of getting plus measurement outcome is larger than a half if Gi is less than Q over 2, and vice versa. So we can simply say the value of the Hadamard measurement outcome tells us whether it's above or below half of Q. Now you might ask why this observation can help us. The answer is it can be shown that the most significant bit of the MSB of the TCF fx is simply decided by whether it's over or below Q over 2. So we can recover the MSB by Hadamard measurements. So what about the remaining significant bits? We know that is running over P. So there should be log P bits in total. And the solution is actually pretty simple. We just need to slightly modify the formula of phase encoding by replacing the 2 here by 2 to the power of k. So in this case, if we measure the state in Hadamard basis, what we recover in the end would be the k's significant bit. And the reason for that is still the periodic nature of trigonometric functions. Well, however, this is still not the end of the story. As shown before, the Hadamard decoding is probabilistic, which means that we only have some probability larger than a half or lower than a half to decode some MSB or some other significant bit. And the probability, success probability is shown here. But in order to pass the pre-image or equation test, we actually need every bit of the TCF to be perfectly decoded. And we have to do that. How can we do that? The idea of doing it is using the repetition code or classical repetition code. You know that we are not allowed to clone states again due to the non-cloning theorem, but we can create states in multiple copies simultaneously because we know the way of creating those states. For example, the state for V times of repetition is shown here. And if we just measure all of them, this will be same as measuring the same state for many times. So we can simply take the majority of them and decide which one should be the correct outcome. But this repetition code is not perfect for our phase encoding. The reason is, if the position of the GI on the unit circle is too close to the boundary of two regions, for example, if it's close to 1, then it will be almost impossible to decode it even with repetition code. Because in this case, you can see from the formula here, the probability of getting plausible 1 is too close to a half. So we call these values undecodable. We have to try to find a way out of it. So how can we solve this problem? This time, unfortunately, actually, we probably can't. But the thing is, it's fine to have some undecodable phase encodings, as long as the fraction of that is sufficiently small, because it suffices for us to ensure with high probability the prover can pass the protocol. So we have the theorem here as another major result. It can be shown that most phase encodings can be perfectly decoded with rather high probability, which is good enough for us. And the idea of the proof is the following. So we consider the phase encoding of every single component by looking at the unit circle here. We can simply exclude those values near the boundary, and we call this excluded region the undecodable region. So if an image of the G function has any of its GI value in this undecodable region, we'll say it is unlikely that we can decode F from the phase encoding even with repeated measurements. So this whole phase encoding is also called undecodable, which is pretty bad. Now so the task for us is to decide how large this undecodable region can be or should be. As we know, we require 99% of the all states to be decodable, which is a constant. And there are m components. So a direct result is that the fraction of undecodable values of each GI should be linear in 1 over m. And as a result of that, the total fraction of the undecodable values of G should be a constant, like 99%. Okay, so in this case, we can just see if we just assume all of the values of the vector is out of this undecodable region, what would be the probability? What would be the success probability of measuring this bit? We know the actually the probability in this case, the success probability in this case is lower bounded by a half plus linear in 1 over m. And so we need to know that by how many times of repetition we will be able to recover all m values correctly with high probability. And that's actually just a biased coin flipping problem. And we can use Hofding's inequality to show that the result would be m squared log m. So that proves our result. Okay, so in the end, let's summarize the pros and cons of the second construction. It features constant depth, of course. And it turns out that the circuit width is significantly reduced. In this case, we can show it's upper bounded by lambda to the power of 8, where lambda is the input size or the security parameter. Furthermore, because we apply this repetition coding in the measurement of the image register, this approach has fortunately some sort of robustness against noise, because that's a very classic way of doing some kind of noise reduction. But for the negative side, the scheme unfortunately only works for a specific construction of TCF, and the computational assumption is LWR, or same as LWE. But this is not a big problem because, as I said, LWR is equivalent to LWE, and LWE is a standard cryptographic assumption, and it has been well studied for more than 30 years, so we can trust it. And another thing is, unfortunately, the required quantum circuit is still pretty wide, unfortunately. Although it's much better than the first case, but its lambda to the 8 is still somehow a large polynomial. So it's not really suitable for these Q devices still. And there are some potential improvements that can be started. One main thing is the parameters are likely not optimal because most calculations we did in this work are sort of lower bounding, some sort of lower bounding. So in practice, probably much less qubits are sufficiently good. It seems also possible to avoid this repetition that I mentioned before. And it is possible if we slightly modify the TCF construction, but well, if you just remove this repetition, this would reduce the qubit number from lambda to the 8 to lambda to the 4. But we haven't thought about this very thoroughly, so I'm not sure about this, whether this will work. And we can also think there might be some more qubit optimal encoding than this large GHZ states used here, which is somehow too consuming. So we leave these problems as open problems of the second construction. So in the end, to summarize our work, we propose two schemes to implement constant depth proof of quantumness protocols. Although they are still not suitable for the NISQ era, they could be a stepping stone towards POQ in near-term devices. It's also worth to mention that our first construction using the strong TCF and our second construction, they also provide an approach to generate certifiable randomness using constant depth quantum circuits. Because the protocol of generating randomness is almost the same as the protocol of proof of quantumness. Well, one last thing to mention is that last year there was a breakthrough by Yamakawa and Zhongji, and they showed that an NP search problem can be solved efficiently by quantum computers. Although it seems their protocol is also not suitable for near-term devices, but that's a good breakthrough that shows that quantum advantage does not really require some structure. Like in our problem, there's some cryptographic structure. So, right, this concludes my presentation. A lot of technical details are still not covered in this talk at all, so please feel free to ask any questions. And thank you very much for your attention.
Yeah, thank you very much for the talk as well. So, as Zane said, now we are open for questions. So if the audience has any questions for our speaker. Okay, oh, I think we have one.
Sure.
Okay, thank you for your talk. I just want to ask very nice question. Is this kind of proving quantum advantage can be applied to like the current variation quantum circuit? Is it possible to use this technique to that kind of problem like VQE? Is the question clear?
Sorry, I didn't hear the last few words. Can you please repeat the last sentence? You said I heard the variational quantum circuits, and what's the last one?
I mean, is this kind of proving quantum advantage technique can be applied to that kind of problem like VQE or variational quantum circuit? Is it possible?
I can't say it's impossible, but you know the key building block of this proof of quantumness protocols is that you need to somehow construct the trapdoor Crawford function, the TCF. It can be dependent on any it can rely on any computational assumption, and this assumption maybe like this the assumption maybe some lead to some function that can be computed by VQE or something like that. But currently, I don't see how to construct TCF using VQE. But as long as you can construct TCF using VQE, then sure, it will automatically become possible to run this proof of quantumness protocols. So I guess the key is VQE. The key is TCF, and so I'm not sure if TCF can be done by VQE. So yeah, that's the answer. That's my answer.
Okay, thank you. Can you tell more about the TCF? Is that kind of assumption really crucial here, or is just one kind of trying assumption?
Okay. Sorry. So yeah. So TCF here is just some kind of function that it must satisfy the properties I mentioned here, and the computational assumption here is that you need to use the computational assumption to make sure it is hard to invert and to make sure it is claw-free. And it would be better that you can construct the trapdoors from the computational assumption that you rely on, like LWE or X square mod n, the Rabin's function, etc., etc. So yeah, and it may be not necessarily even a function that can be clearly written. So maybe somehow you can map it to a more abstract function that can be implemented by TCFs. That would also work, but that would be a lot of possibilities in that. And I can give you an example of TCF here that is used in our second construction of phase encoding. It is just like this. This F here is a TCF, and it has two. It has two for every image. It has two pre-images, 0x and 1x minus s. So as long as you can do something like this using whatever platform, you will be able to do POQ basically. So it's not it's not special. It has special properties. It's just that like a platform or a scheme that you can use any computational assumption to construct it as long as you can do it. So not every computational assumption can lead to TCF, but as long as you can find it, you can build it.
Okay, thank you very much.
You're welcome.
All right. Do you have other questions? I think perhaps we do not. So
Sure.
I wanted to thank you again for coming here and talking to us and presenting your work.
Thank
and
you.
Let's all. Thank you very much. Let me stop the
Thank you.
recording. Thank you.